Okay, for today we're going to jump into what looks like a totally new and different topic from what we were doing, but it's going to relate all together by the end of the chapter. So, we're jumping back to the beginning of the chapter and looking at gravity and the theories of gravity and all that good stuff and Newton's law. So, we'll tie that back in with circular motion after a few days. So, it will come together. The plot threads will converge. What we're going to look at today is this right here, Newton's law of universal gravitation. Tomorrow or the next day, whenever, we'll look at applications of gravity and how you use the equation a little more. But we'll first start out just with the law of gravity. By the time we're done with that, we already did circular motion, and the threads will come together down here with planetary motion and orbital mechanics. Okay, so first of all, gravity is an attractive force. Any mass will attract any other mass. Doesn't have to be planets. Any two masses will attract each other. So Manny and Hayden are right now attracting each other. Of course, their distance is pretty large, so the attraction force is relatively small, but we're not surprised by that. The other forces out there, like electric force, magnetic force, work in very similar ways to gravity, but they're much, much stronger forces. In order to have a noticeable gravitational force, it's such a small force, you need masses on the size scale of planets before you really notice it. Okay, now, if you go back to the day, the big question was, why do things fall? Ask Aristotle, who would say it is in their nature to fall. And so that wasn't very satisfying. The first guy to really question that was Galileo, and he was kind of an arrogant jerk about it. He'd ask people why things fall, and they say, well, because gravity, and you say, that's not an answer. That's just putting a word on it. You're stupid. They threw him in jail for that kind of stuff, because he annoyed the Pope. It wasn't until Newton came along and really, really thought about it. Strangely enough, he came up with the ideas of this while the schools were closed because of plague. That sounds vaguely familiar. But according to his own story, he was wondering what held the moon in its circular orbit. Why is the moon circling the Earth? Surely there's a centripetal force there. He knew that much. But what's providing that centripetal force? He claims he was sitting under an apple tree because he's no farmer, so he was just relaxing, and watched an apple fall and realized the force that pulled the apple down, the gravity force, was the same force that pulled the moon in its orbit. And from that, he deduced the law of gravitation. He calculated based on the moon's apparent distance what the gravitational force must be there, and figured out that the gravity force changes with the square of the distance. So here F is the force of gravity. It equals, now notice down here you got distance squared down there. Again, that's empirical because he knew based on the moon's distance that the gravity force was significantly smaller than on Earth. Not the way to account for how small it was by squaring the distance or the radius. He also knew that it depended on the mass of the object. The gravity force on an apple depends on the apple's mass, obviously. But there's equal and opposite reaction pairs. So if the Earth is applying a gravity force on the apple is applying a force on the Earth as well. Same exact value of force. Why does the apple fall but not the Earth? The Earth is a little bit more massive. So he realized that force, though, depends on the mass of the other body, the Earth. And since they're both equal, the force must depend on both masses. So the force of gravity depends on the mass of body 1, the mass of body 2 multiplied together. The Earth and the apple, the Earth and the moon, Manny and Hayden. But it also depends on the inverse of the distance squared. So force is proportional to m1, m2 over r squared. That's Newton's law of gravity right there. People often say, well, what did they do before they invented the law of gravity? Well, obviously gravity still existed. They just didn't know it worked this way. So There's the law of gravity. Notice we're saying force is proportional to those quantities. To make it equal, we need a proportionality constant. That's what this capital G is. Capital G is the universal gravitational constant. It's the proportionality constant between Newton's force and these mass and radius values that we're plugging in kilograms and meters and all that. So G is really just a proportionality constant. And it has a value throughout, the same value throughout our universe everywhere. It's not just G is on Earth this value, but on the moon some different value. It's the exact same G everywhere in our universe. So you go to Andromeda and it's the same G. That's why we call this the law of universal gravitation. By the way, that was a huge, huge deal at the time, because back in those days, the heavens were different from the Earth. It wouldn't even have occurred to guys before Newton to wonder about the moon and gravity, because they would have said the moon's going in a circular path because it's in the heavens. And the circle is the most perfect shape, and the heavens always do things perfectly. Earth has gravity. Well, that's an earthly force. What made this law of gravity such an important thing to physics is that Newton showed that the laws of the Earth governing gravitational acceleration of things falling on Earth were exactly the same as the laws of the heavens. That same gravity force that made the apple fell was the same force that made the moon stay in its orbit, and the Earth in its orbit around the sun. The Andromeda and Milky Way co-orbiting each other. So making G a universal constant showed that the heavens were nothing special. They were just an extension of the same laws of the Earth. A generation earlier, he would have been burned at the stake for that, like Galileo almost was. But in his day, they kind of relaxed a little bit, and he can get away with that. But yet, that's why we call it universal gravitation. So, in Newton's day, they actually couldn't find the value of G. Because now, if I go back, actually, you'll notice, take the apple falling to the Earth. We know the force of gravity on the apple. That's the apple's weight in newtons. mg, right? Whoops. We know the mass of the apple. Call that m2, whatever kilograms it is. We know the radius from the center of the Earth. Notice not how high above the surface, but how high above the center of the Earth it is. So you have to add the radius of the Earth plus the height above the surface, which usually that's irrelevant compared to the radius of the Earth. So we know the gravity force in newtons, which is just the weight of the apple. We know the mass in kilograms of the apple. We know the radius from the center of the Earth. If only we knew the mass of the Earth, we could find the value of this universal constant. But back in Newton's day, they had no clue what the mass of the Earth was, and so they were stuck. They had no way of figuring out what G was. Later, a guy named Henry Cavendish did a rather famous experiment that allowed him to calculate what G was. We'll look at that experiment in the next lecture. You can't wait. But they found that G is equal to 6.67 times 10 to the minus 11th. Look at the cool units on that. Newton meter squared per kilogram squared. That has to be because, notice, your answer, going back to the previous slide, has to be in newtons. This is in meters, or kilograms, so kilograms squared. This is in meters squared. You need to cancel out those meters squared in G. You need to cancel out those kilograms squared underneath G. So putting it all together, you got to get newtons for your answer. This cancels out the meters for the distance. This cancels out the kilograms for the masses. So it's an ugly unit, but you really don't have to worry about it. It works. As long as you do everything in SI units, this value of G will work and will give you newtons for your answer. Notice that 10 to the minus 11th. It's a very tiny value. That makes G a very small force. It makes gravity a very small force. If this G value had been a larger constant, 10 to the minus 5th or some such, gravity would be a much, much more powerful force, which means standing on the Earth, you'd be smashed. It would be literally thousands of times more gravity than we have now. The fact that it's this small makes a difference because that means we need planets in order to have gravity happening. On the atomic scale, we ignore the gravity force completely. We don't worry about the gravity of a proton attracting the electrons around it, because this value, 10 to the minus 11, makes the forces so small that they're just unmeasurable, and the electric and magnetic forces totally dominate. It's not until you get to the very large scale where the gravity force becomes enough to dominate and become noticeable and affect behavior. So in the large scale world, gravity forces dominate. In the small scale world, electromagnetic forces dominate. And so the value of that constant kind of makes that be so. Now, okay, so notice it is a vector equation. Force is vector, the radius is a vector. The force of attraction between any two masses, and notice gravity force is always attractive. There's no such thing as negative gravity, at least not yet. So if you have two masses, the force of gravity between them is always along the radial line between them, pointing toward each other. And again, note that they are just a third law action-reaction pair. Mass 2 is applying a force this way on mass 1. Mass 1 is applying a force that way on mass 2. They are exactly equal magnitude. Third law dictates that has to be true. And that's why it's m1 and m2 in the equation down here. If these two have similar masses, their accelerations will be similar. So if m1 and m2 are the same mass, same force on same mass gives you same acceleration toward each other. If m1 is much greater than m2, it's still the same force. So that force on tiny m2 is going to cause a large acceleration. That same force on massive m1 will cause much less acceleration. Again, it's why you fall to the Earth and the Earth doesn't fall toward you. I guess technically it does fall toward you at an acceleration of 10 to the minus a bunch, which we don't notice that. Okay, so they do point out here what I said already is the weakest force of nature. We'll actually compare the four forces a little later on and how they interrelate to each other. So again, if we were to calculate the gravitational force between Manny and Hayden, given their masses and their typical distance from each other, we'd find a force of 0.000 something newtons. And the friction force on their feet is enough to prevent them from falling toward each other. Even if they were frictionless, they'd accelerate toward each other at 0.00 something meters per second squared, and it would take years to notice any perceptible changes. If you use something like a planet, now the gravity force is strong enough that they move perceptibly and you get nice orbits. Okay, here's a quick sample problem, then I'll leave you alone because I only have 2 minutes before my recorder stops recording. They give us a 45 kilogram girl and an 11 kilogram dog, and she's taking the dog for a walk. They're 1 meter apart. How much force is the girl exerting, gravitational force is the girl exerting on the dog, and vice versa? All right, well, the mass of the girl is 45, the mass of the dog is 11. Plug them in for the m1, m2. The radius is 1 squared. Plug in g. And on my slideshow, it's hard to see the negative on there in the exponent. That's negative 11th, obviously. It's there, but I don't think you can see it. When you plug all the numbers in and try this to make sure you get it, you get 3.3 times 10 to the negative 8th newtons. Again, that's a negative 8. I can't see the negative here, but it's there. It should be there. So the girl's applying on the dog a 3.3 times 10 to the negative 8th Newton force. And so, again, the gravity force holding the dog on the Earth is much greater than that. The friction force keeping its paws on the pavement is much greater than that, and so the dog doesn't just accelerate toward the girl. Notice the dog's exerting the same force on the girl because they're action-reaction pairs. Okay, this graph, real quickly, is showing how, since it's a distance squared, inverse distance squared graph, how gravity force drops off with distance. As you move further away, the force drops really fast and then it levels off. At an infinite distance, your gravity force becomes 0. We'll talk more about that later when we talk about potential energy and gravity. But my time is pretty much up for today, and we'll stop with that. I'll give you a worksheet to do. Download that, do it, and we'll continue tomorrow. I'll see ya.